keynote will be delivered by Professor Ajay Kumar Shukla, Professor of IIT Madras, Department of Metallurgical and Materials Engineering. I think steel people will be more benefited from his lecture because he is actually the steel person. He worked in the Durgapur Steel Plant earlier. After that, he switched over to academics. And I think any queries related to steel making, and also he will briefly discuss about the CSIRO and IIT Madras collaboration. So without wasting my time, I am inviting Professor Ajay Kumar Shukla to deliver.
So, good morning everybody. Thanks Professor Mandal for organizing such a wonderful program on decarbonization of iron and steel area, which is the need of the hour. Basically, after several years, I have been in Durgapur, and basically this is my very old city. I have been here for about 1 decade while working in Durgapur steel plant, in steel making shop. So, anybody from DSP? From which?
Same shop.
Oh, okay. Yesterday. Okay. Yesterday I talked to you.
And your chair has been taken by him.
Yes. So basically, I'm in IIT Madras since last 12 or 13 years, working as an academic. You are from ISCO one?
Yeah.
From which department?
I am from power distribution, he's from filter plant, and one guy is from blast furnace.
Oh, who is from blast furnace?
Yeah, he's coming, he's from Boston.
Okay. So it is very great to find out the blend of scientists, experts from industry and from academia, working in different areas of iron and steel making supply chain. So basically, just today my discussion will be focused only on the kind of capabilities which I have, in fact, which my group is having, my group had been involved over the last several years at IIT Madras, and as well as I mean to say, due to sudden experience in industry and ongoing collaboration with the industry and institutions, many research organizations of international repute like CSIRO, with whom I am working on one of the potential projects of iron ore beneficiation, particularly particularly utilization of synthetic iron ore in the surf furnace. So this is the general overview of my activities in my group, that is also named as Center for Pyrometallurgy very recently. Okay, fine. So this is the general overview of the research theme of my group. So basically, this is I started my journey from this process methodology, particularly modeling, control, and optimization of iron steel making area, because initially I was working in the steel making shop at the steel plant, and I took a very deep interest in automation system, and which was having a lot of control models which were the part of level 2 automation control system. And since as a fresh graduate from IIT, I was having a lot of inputs and background because of my education from IIT Kanpur in those days, and I found it very fascinating. So that is from there I developed my interest on the modeling, control, and optimization related aspect. That could be, I think, that involves a lot of mathematical concepts, understanding of the concepts related to the process metallurgy, and then wrapping all of them into the form of a mathematical model, and then all those things. A lot of programming is also required. Like in those days, I was doing programming in Fortran. Then later on, I started doing programming in MATLAB, and then, of course, now there are a lot of programming tools which are available, particularly to thermodynamics and all kind of flow resource optimization related. So lot of tools are there, but the underlying, what my focus is not just to talk to you about what software has been used, but my more focus is on underlying very basic concepts and principles which are very much relevant to all these areas. So this computational thermodynamics and its application to high temperature metallurgy process. So obviously thermodynamics, understanding of the high temperature thermodynamics is an integral part if you want to for any extractive metallurgist. Then application of computational models. Now earlier they were called as data-based models. Now people call it artificial intelligence and AI and machine learning based models. So steel plant actually is having a lot of data actually, and basically there is no shortage of data, and data are coming from everywhere. They are coming from the field equipment. They are coming the data from one batch of the process to the other batch of the process. Data are coming every second, and transient data in terms of various measurements like pressure, temperature, flow rate, composition of waste gas, all those things. So basically we are having a lot of data that is being generated, and somewhere those data are going to be a valuable tool to understand the behavior and dynamics of the process actually. And earlier people were thinking about doing that, but the things were difficult because of the limitation on the computational capability of the machines. But today, we are having high computing machines and a lot of development on the front of machine learning. So basically, we can use those data for understanding the process and its behavior, its dynamics, and suggesting the future, most appropriate way of working in an efficient manner. Of course, today people are talking about sustainability and green metallurgy, whether it's a green iron making or green steel making, everything is green actually. So that is what we don't want carbon anywhere. But how to get rid of carbon in a step-by-step manner is also a challenge, because all the past technologies have been developed based upon coal only. So that will take time, but that has to be done. And then one of the projects which I have recently worked on, the microwave processing and beneficiation of metallurgical materials, particularly lean iron ore, chromite ore. And now I have also been involved recently in the study of critical mineral extraction and refining. I do not have any project right now, but yes, we have a scientific capability, and if subject to a condition, if there is a tie-up, definitely can get involved. So the overall, my research activities are based upon understanding of the process reactions, mechanisms, associated with thermodynamics, kinetics, heat and mass transfer control phenomena in high temperature process related to ferrous and non-ferrous. This is my overall capability of the micro. And the research not only covers mathematical modeling and laboratory experiments of high temperature industrial process. Laboratory experiment that also involves the data coming from the large scale industrial process as well. If I develop any model for a large scale process like blast furnace or oxygen steel making or matrix process. So basically we are always looking for those kind of process where this kind of expertise could be applied and process could be understood, and the operator on the shop floor could be given the guideline just based upon a certain concrete scientific understanding and fundamentals. This is what so the overall theme of my group can be divided into two parts. The first is application of quantitative approaches in process metallurgy and steel making, that is coupling of thermodynamics and kinetics of the high temperature reactors, and translational research, that means development of new innovative technologies based upon, starting from in a step-by-step manner, based upon understanding of the raw material first, and then doing certain laboratory-based experiment, developing the proof of concept, and then trying to think about scaling up in a step-by-step manner, and that is followed by bench scale or pilot scale applications, and then this is how I think my group current mandate and future plans are there. I do not know how much up to what level I will be able to go further. That depends on the support from various institutions, funding agencies, and others. But I am always open to the ideas which have been defined in this very broad So far, these are the projects which I have indicated earlier, or this red one are, I think, the ongoing project which have been recently been completed or still ongoing. That means comprehensive mathematical modeling development of PO steel making process, modeling of minerals iron making process, industrial validation. Okay, so these are the projects which are the part of the PhD. Yes.
Can you kindly explain the number 3 point? What kind of modeling has been done in iron making, mostly related to blast furnace?
This data-based modeling approach to control iron. Basically, I think sometimes back we have taken some data. Actually, as far as our capability is concerned, we are having the capability to model and simulate the entire blast furnace reactor by dividing it into number of zones. That means, the blast furnace is a combination of gas solid reactor on the top, followed by smelting reactor, and then that is also connected through the combustion reactor, and all their mechanism and all their things could be integrated together in the form of mathematical model if you can develop, or in the modules, independent thermodynamical module that could be developed by using some thermodynamic software, and you can integrate them together by kinetic flow of streams. So we have the capability that if you are having the industrial data, based upon that data, it is possible for me to predict that how much amount of coke is actually going into direct reduction, how much is going into indirect reduction, and what is the efficacy of. So basically, if you are using a good quality coke, actually, so obviously the fraction of indirect reduction would be more, obviously, and that is more. Then obviously you will require lesser coke for the smelting direct reduction, and then your overall coke consumption will come down. But the same thing is automatically getting reflected in the waste gas also. That means if the process is not running well, then you will end up with high CO percentage, high temperature of the waste gas. So basically, we are having a comprehensive framework to study the blast furnace phenomena, to do the sensitivity analysis. That means that if you are going to change this parameter, then what is going to change that parameter, then what is going to happen. And if you are having any ongoing industrial data, we can predict the health of the process, that whether your raw material utilization is going in the proper way, and if it is not going, then we can identify that okay, there is a problem with the iron ore, there will be the problem with this part, or there is a problem with that part, there is a problem with the coke reactivity. So these things can be, so basically these mathematical tools are very much relevant in extracting out those information. In fact, it is also possible that, for example, I will not tell the name of a steel plant. So I took the data from them. So this is just for academic investigations, no formal project. So I took some data from the steel plant, say that okay, for some of my students is working on it and they want to I want to demonstrate them. And then when I did some calculations and did perfect input or output balance, then I found that whatever coke rate they were projecting, I think that is not matching with the overall balance finding. But I mean that means that either your output should be less, you are projecting more, or whatever. So those kind of things could be found. So a lot of possibilities are there.
So sir, presently this model is working, or is it in a theoretical state? This model?
Basically, working means that if any industry is interested.
Means if we are interested and if
no, so for that, if you are interested to provide your data, for example, you can provide the current data of some of the blast furnace, which is either running very smoothly or either running not smoothly. I can just investigate those data by using those tools, but provided that those data should also be accurate. But again, whether the data are not accurate or whether there has been some discrepancy in the data, that can also be identified with the help of this model.
okay.
So basically, I'm just telling you because if industry does not want to reveal certain things, then do not give us the data.
No, the thing is that if we want to collaborate, and we want to use,
yes,
definitely the data has to be a sanity one, because I cannot give you data which is not true and expect a result to improve.
No, basically, if you want certain changes in your outcome, or you want the better utilization or better specific consumption of some of your input raw material, or if you want to bring down your coke consumption. One of the vital factor is the coke rate.
Inefficient.
So if you want to bring down the coke rate, then obviously you have to. But again, this is not just limited to the modification in one front, because the person who is operating the plant, he knows better. There are a lot of things which are depending on the raw material characteristics, raw material size distribution, the burden preparation, the blending, as well as the sequence of charging, all these things. So basically the problem could be identified. What problem is there, that could be identified. Where the particular stress should be focused, that could be identified. But then it is the job of the steel plant operator to try various possibilities, starting from their changing the raw material configuration, and then in a step-by-step manner looking at various other aspects. So any kind of process improvement is not so straightforward actually, but yes, we can identify certain things. Okay, yes. And then again, what I am talking about, database model. So the fundamental model, they are working in association with database model. That means that you cannot incorporate each and every part of your process in a fundamental model. Particularly, what are your heat losses? A lot of heat is being lost and the process duration is longer. If you cut down the process duration, your heat loss could be brought down. So any process could be made more efficient if its kinetic rate has been increased or its time could be brought down. So these are the things which, how you can bring down the time duration of the process. You need to understand the kinetics of the process, you need to understand the mechanism of the process. So these are the things, somewhere it is going to help everywhere. Not only blast furnace, it is in steel making and ferroalloy production, or wherever there is a, I think, high temperature mechanism involving gas oil reactions or smelting. So that is the thing. So right now, okay, so sorry, I take a longer time. Maybe I will finish quickly in 5-10 minutes because Dr. Nosal is waiting us. Okay. So this geosteel making process, mid-rex process, micro-assisted beneficiation of lean quality iron ore. This is, I think, Government of India sponsored project. Actually, this helped me to create a laboratory which we have named as Center for Pyrometallurgy. Then this project we have started, I think 2 years back, on the study of reduction kinetics of Indian iron ore in the loose powder form and as well as the pellet form using hydrogen actually. So this is a project supported by Department of Science and Technology, Government of India. It is still going on. I think the Sham actually, he had worked as his MTech on this project actually. So basically he had already worked on this project. That is why he has been trained on this hydrogen experiments, and it is helping. And this is the project which is, I think, most important project is behavior of synthetic pellet in DRI SAT furnace. That is funded by CSIRO Australia, and we are working with Dr. Naushad and his team for last 1 year. And in this project, actually, this synthetic iron ore, actually, that is a very common problem for India also and for Australia also. And we are just trying to study the Australian iron ore from different perspectives. That means starting from comprehensive mineralogical studies, then rigorous characterization, then understanding the raw material, then the understanding the raw material under thermal conditions, and then converting this pellet, this synthetic iron ore in the form of the pellets with different operating parameters, and then investigating them under a hydrogen atmosphere, the same way we did it for Indian iron ore. And now that those experiments are going on and very interesting results and findings will come, we want to just make sure that these iron ores could be used effectively in DRI process. And if up to what extent they could be used and what are the challenges, what are the limitations, this will be the part of this investigation. Okay. So in pictorial sense, the overall group activities, they are involving on one front mathematical modeling, and then development of the mathematical models, and then wrapping them in the form of graphical user interface, because if you want to deliver it to industry, they want to see it in this form. Then certain experimental facilities on smelting front also, on reduction roasting front also, on sample preparation front also. So this is the news actually. I think in Business Standard last year came, where we worked with IIT Kanpur. on the project of beneficiation of lean quality iron ore by using microwave assisted reduction process, where the proof of concept was established in the laboratory and followed by its further demonstration and testing at NMDC at 20 kg of bench scale. And we were able to convert a 45 grade of lean quality iron ore, Indian iron ore, to blast furnace grade 61-62% grade, with I think with a recovery of 70%. So that is the outcome of it. So I will just quickly just give some overall. For example, it will address your query that we are working on high temperature process, because this is the area where I've been engaged for a very long period of time, and my understanding and modeling approach is very simple actually. Very simple in the sense that the high temperature process, if you want to study any high temperature process, you need to understand certain basic things, starting from overall heat and material balance, and thermodynamics of the process and kinetics of the process. These are the things which are very much important, and you need to understand and their interaction and their coupling in whatever possible way. And then for a complex process, that may be based upon the permutation and combination of the similar kind of building blocks. Okay, that I will just explain in the next slide. So the high temperature process basically involves heating, melting, dissolution of raw material flux, because this is the first step that has to happen. So, and then there is a dynamic interaction between slag, metal, solid and gas phases existing at very high temperature. This is very much common for all the processes, whether it's a blast furnace, VF process, or whether it's steel making or secondary steel making. And then basically we also need to have understanding about the reaction chemistry of the process, which involves thermodynamics and kinetics, but their coupling may be different. For example, if you are having the gas-solid reaction, the coupling of thermodynamics and kinetic understanding may be different, because that may involve diffusion-assisted mass transport control phenomena as far as the kinetic limitation is concerned. And if you are talking about smelting process, then that may involve slag-metal reaction, where the convection in the slag or convection in the metal may be the rate limiting step, and you can appropriately just involve certain mass transfer coefficient and equations, and you can just mathematically demonstrate them. And also this is also coupled with the dissolution of various solids which are adding, like scrap lime. So they are also going to add to the volume of the metal and slag at every time interval. So this is how I mean to say that you want to develop a transient development of a process. So you just divide the process into time steps and then you integrate all of them. Of course, if you want to study the convective mass transfer, then obviously somewhere the idea of computational fluid dynamics is coming into the picture, or otherwise the heat transfer is coming into the picture everywhere, whether it's a solid state diffusion, heat transfer, or whether it is a convection state heat transfer. So basically these models could be delivered in industry with multi-level automation control systems. So for example, this in the integrated reactor approach, this is the example of slag metal reaction. So in the slag metal reaction, we know that this is the interface of metal and slag, where there is a concentration gradient which is existing on both the sides, and that is existing because of lack of mixing in either of these two phases. So basically, if the mixing is very good actually, if a properly mixed reactor, then this bulk concentration should be equal to the interfacial concentration, and both should be in thermodynamic equilibrium in overall sense. But this is not happening in practice actually, because because some part of the reactor is thoroughly mixed, some part of the reactor is loosely mixed. That depends on kind of turbulence. For example, if you talk about oxygen steel making process, that is having very rigorous energies being evolved because of the evolution of carbon decarbonization, carbon monoxide bubbles. And also, for example, the harsh region of the blast furnace, that can also be assumed in almost thermodynamic equilibrium between slag and metal. But for example, if you talk about ladle actually, so in the ladle, the slag metal equilibrium may not be there. It will require a certain duration, like it will require a lot of bottom purging and stirring, and you will need to. So basically, in mathematical sense, you need to just write down the mass transfer equation and a balance with the overall bulk actually in this form. So this is how the people have modeled this process since long. So you just need to couple thermodynamics and kinetics together. But now the same thing can be done with the help of any kind of computational software. For example, whether it's a FactSage or whether it's a MaxSim or anything. So there would be multiple number of reactors, for example, bulk metal, bulk slag, Okay, so basically they may be in the non-equilibrium reactor, but there could be interface which is in thermodynamic because of high temperature, the interfacial compositions will always be in thermodynamic equilibrium. That means these two compositions can always be regarded as thermodynamic equilibrium actually. And so this interface will be represented as a thermodynamic reactor, and these flow of streams could be defined at every time step in certain fraction or certain rate, and that could be somehow they could be related to the mass transfer coefficient. So this is for a slag metal reactor, slag metal reaction. The similar kind of logic could be given for gas solid reaction as well. So in this way, for example, for oxygen steel making process, we were able to develop integrated flow sheet model like this way. So there are, I think, two thermodynamic equilibrium reactors, followed by there are two non-equilibrium reactors, bulk reactors, and there are flow of streams which are getting circulated between all of them. And this is the reactor, for example, any kind of SAT furnace. So here we are having gas solid reaction predominantly, and here we are having the slag metal reaction or gas solid reaction. So for gas solid reaction, we adopt the similar kind of approach, but we are just taking some another kind of we are applying another kind of system where there is an interaction between the rising gas and as well as the descending burden, but all of the gases are not getting reacted to the burden. A part of it is getting bypassed because of the kinetic limitation that is assisted by the diffusion in the solid, and accordingly we have mathematically translated it. And we have developed a model. So basically, in the overall sense, our group computation expertise involves thermodynamic kinetic based model using fractal microprogramming. We are also using ChemSheet, where the fractal model database could be integrated in an Excel based VBA solver package. Then also the first principle based model using MATLAB, Python, flow sheet based model, MetSim, ChemSheet, and also Microsoft Excel is also having the VBA based modeling capability. So these are the snapshots of the mathematical model which we have developed in our group. This is, I think, the snapshot of model. So these are certain geographical geometric snapshots which were delivered to industry. So this is basically a virtual model that we have developed for this one demonstration for oxygen steel making process. So for oxygen steel making process, the behavior of the reactor in terms of its evolution of the carbon, silicon, I think bath composition, slag composition, volume of the slag, waste gas, everything could be just estimated by applying the similar approach. In fact, I think most of the information is available on my YouTube. Actually, I have made these calculations, and one can just have a look at it.
So can you try and go to the previous slide once?
Which one?
Previous slide. Can you take a snapshot? The next one. No. Forward. No, more towards the end.
Next one.
No, forward.
No, forward.
Okay, back.
Forward, not back.
Forward.
Oh, sorry.
This one.
No, next one. This one. Can I? Thank you, sir.
So now just I am quickly going to give the idea about my laboratory and the experimental facilities which I have. So earlier I used to call it as a process metallurgy lab, then later on we named it as a Center for Pyrometallurgy when I got the funding from. And we have so from that imprint project we have created this laboratory. So this lab is having, for example, here these are magnetic separators. I will just show these equipment one by one. So this is like a Davis tube, high intensity magnetic separator. For then there are certain number of furnaces, horizontal tubular furnace which can go 600 degrees centigrade, vertical tubular furnace where these hydrogen experiments are going on. Okay. So from here, this weight of the sample could be measured from the bottom actually, from the rod, and the sample could go into the center, and we can control the atmosphere in terms of carbon monoxide, hydrogen. Okay. For carbon monoxide, actually we don't use carbon monoxide cylinder. We have not done any experiment with carbon monoxide, but we are having another furnace, tubular furnace, where we have proposed to heat coke at high temperature and pass carbon dioxide from it. So in this way we generate carbon monoxide. These are the muffle furnace. Then Then I think microwave furnace. So this is the I think video. I will show these equipment. So the experimental facilities are as follows. That is high temperature hybrid microwave furnace which can go to 70 degrees centigrade. Then high temperature control atmosphere vertical tubular furnace, which is kind of TGA furnace. This can also go to 70 degrees centigrade. Gas analyzers, CO generator tubular furnace, jar mill sieve. So these are, I think, these 20-ton cold pressing machines for making the pellets. Magnetic separator, wet high intensity magnetic separator, Davis tube. Then this basically we can also control the atmosphere of internal atmosphere of this furnace. So for that it is connected through hydrogen and argon and CO2 cylinder, but that is passing in between from the coke, so it emits CO. Muffle furnace. These are the two smelting facilities. That is induction plate furnace for melting of the steel and slag, and induction rotating cylinder furnace. So this is for the melting purpose, and this is the last one is for doing the dissolution study actually. That's why just I will show you quickly. So this is a hybrid microwave furnace. Okay, this can be controlled from the HMI and computer. So this heating cycle, everything could be fixed in this furnace. This is the vertical tubular furnace. This is an important furnace which we have used extensively for our iron ore reduction by hydrogen.
BBCC is the supplier of the equipment. BBCC.
BBC.
Is Chennai based or where is it?
No, it's Chennai based. Yes. That is, I think they are working on Make in India, and they have been working very. So basically, this is the furnace which we have used. So these are the components of furnace. We are having a gas cleaning system, and this is where we are having the cooling system here for this upper tube, and this is I think the rod actually. Rod is connected to the wave base, and then this is connected to the computer where the weight of the sample is getting recorded every second. Okay. And while the reaction goes on, so there is going to be weight loss. So this data, which we store in the form of Excel sheet, that can be later on studied to understand the kinetic behavior of reduction phenomena of iron ore under different conditions. These are the, I think, magnetic separation unit, Davis tube. You must be knowing about it. This is the hot-ended tubular furnace, which is also assisted with vacuum. Actually, we have not done it so frequently. But also here we have control atmosphere facility. That means we can control atmosphere, but we do not have any kind of measurement while process goes on actually. But we can do it under vacuum. We can use this one also. This is a tilt induction furnace. But anyway, I just show you the video of the tilt induction furnace which we have operated over there. We tried to melt it with the blast furnace slag, and also tried to investigate one project actually, that is dephosphorylation induction furnace actually. We did 1 or 2 trials to see that what is going to become the effect on the phosphorus of the hot metal or DRI.
By putting center?
No, we have just used a synthetic, I mean to say that we have used a combination of limestone, silica and iron ore together to make a slag of CO, FeO, SI2 kind of system. But again, I think the dissolution is taking longer time. Lot of silica is getting evaporated. So we are looking for some already ready-made synthetic slag that if you add it, it is getting dissolved and it is able to capture the phosphorus actually. So this is we were not able to run this equipment so extensively, but we are having that capability. That we can, this is a 5 kilogram furnace which can go to 600 degrees centigrade. So this is a tapping of, I think, melted blast furnace slag actually. This is the first time we're taking a photograph. And this is the rotating cylinder furnace. So here what is going to happen is that here there's I think 1 kg crucible which can have I think half to 1 kg of slag or ferroalloy, anything could be melted till 1600 degrees centigrade. And this is the cylinder, rotating cylinder. So that at the tip of the rotating cylinder, one can fit any object which you want to study from dissolution point of view in this liquid pool actually. So basically this could be rotated at various RPM, and then the sample of the melt pool could be collected at a certain time interval. And then so you can understand that at what portrayed. For example, the line resolution in slag. So one can have a line sample, cylindrical sample fitted on the top of the cylinder, dipped into the already melted slag, rotated at various RPM, and then I think these kind of experiments are earlier taken place, but now, or the dissolution of graphite into this iron melt. So those things could be done. We were not able to run this equipment because of non-availability of the appropriate staff actually, but definitely here, I think our objective is that to demonstrate that we are having these capabilities, and if any industry partner, anybody is having any kind of possibility to involve with us in this work, definitely I will welcome it. So just for example, this is how this setup is looking like actually, in actual sense. This is first condition. So here actually, this cylinder is rotating. From here we can control the RPM. From here there are a number of holes. So from here atmosphere, for example, one port would be for argon, so you can create inert atmosphere inside it. We can also insert, I think for sample taking, the rod could be inserted from there at a different time interval. Thus the melt sample could be taken and that could be characterized later on. So this was all about actually. But just I just show you one video, which is I think. So this is the operation of a vertical tubular furnace while the hydrogen experiment was going on. Okay, so just I took one video so that I think you can understand that what. So here this experiment is taking place at 900 degrees centigrade in the vertical tubular furnace using hydrogen and hydrogen percentage. So right now we are using the combination of hydrogen and argon together. Hydrogen to 10%, 20% and 30%, rest is argon, and accordingly the time duration and the flow rate that has been decided by stoichiometric calculations and by just putting some utilization ratio. For example, earlier my student did the experiment for Indian iron ore. Okay, so there we were able to find out that what is the utilization ratio of hydrogen for Indian iron ore. Okay. Now it is the function of iron content. For example, if it is a better iron ore, then obviously that ratio will be lower. If it is a lean iron ore, so that will be more. So accordingly, we have used those parameters, those understanding to decide the duration of the experiment. And accordingly, we did the experiments and we are getting the results to investigate them further.
Can you capture the off-gas
Yes, we are having the capability, but now it is not working actually because we need to calibrate it. In the MTech project of my student, it was working, he did it. But I think now for this one, it's not working. We have called a supplier, but definitely we are having this setup is very much useful, and basically we can do a lot of things. It could be a complete input-output balance. That means if you measure the waste gas CO and CO2, it would give you a complete balance. Okay.
After this reduction is completed, we have estimated below.
No.
Additionally, Ministry of Steel Project, we have
Okay.
completed, but it was not. Maybe a method or the method to be there at the bottom, and we study the slag metal interactions and all those.
No. So basically, you will start with the iron ore pellet, and that will be, I think, a bed of pellet that has been reduced by hydrogen. Okay.
That will be loaded after reduction. It will be loaded.
Loaded at what temperature? Same temperature or cooling. Okay. And then directly charged into the metal. But then are you using any flux also into it?
No, it is only to study through the induction furnace. Below this we have
Okay.
a coil and it gets melted, and then you can study what kind of evolution is taking place, separation of.
Okay, so basically in that case there is a possibility of generation of some amount of slag also. So, but again, if the iron ore quality is not good, then I think more slag, and then also what will be the purity of raw material? You may end up with a high phosphorus. Then you need to just design the flux chemistry in order to create a better distribution ratio of phosphorus and sulfur and those things. So it is a matter of, I think, another fundamental study. Of course,
This FEO will be very high.
so obviously in that case phosphor, it will help in dephosphorylation, but for desulfurization I think we need to. So we need to just have a data actually. Basically from fundamental perspective, so I started from fundamentals actually. So as I said, that it could be any process. For example, I was contacted by a federal industry that is in the Balasore few days back, and they said that they are having a ferrochrome reactor and they want to just want me to study it and just suggest some, because they were able to increase their chromium recovery and most of the chromium is more chromium going to the slag and they are not able to release this. So they wanted to improve it. So before getting into the project, I said that okay, please send me some ongoing industry data. I need to understand and study them because I know that how this ferroalloy process, whether it's a production of ferrosilicon, ferromanganese or ferrochromium. Fundamentally speaking, this is almost similar to how the blast furnace works. In fact, I should say that if you are an expert in blast furnace area, I think there is no doubt that you will be the expert in any kind of high temperature metallurgical process because the blast furnace controls all associated phenomena which any high temperature process metallurgy is supposed to know. So just since I have never worked in ferroalloy project earlier, but then I asked the industrial data, and then I took those data, and then I developed a similar kind of multiple reactor based model for ferroalloy reactor as well. That means, of course, the top region here also the gas solid reactions. So obviously there could be you should end up with the chromium carbide before it should go into the smelting stage. And so the similar kind of things I have applied, and then I studied their model with that model, their data, and then I found very useful findings. And then I suggested them certain things which they have appreciated, and then I said that okay, now I want to submit a detailed proposal, and I want to look into your things more rigorously. Then it also involves the understanding of the whole furnace configuration because the heat losses are also going to contribute to the losses. So what kind of refractory lining are they going to use? What kind of coating they are going to use? Or basically for how many life they are. So this property of refractory lining is also going to affect the fuel consumption. And there are a lot of, for example, in electric arc furnace or in submerged arc furnace, the voltage current characteristics, how this current is being transferred from arcing zone to the metal zone, what are the mechanisms. All these things are having, they are subject to the fundamental investigations by the appropriate experts actually. So with this I want to conclude, and then finally words I want to say is that no matter whatever we do, but always focus on fundamental concepts actually, because that is going to be very helpful, and even the experimental results and data can provide a better insight if you look at the process from very basic fundamental perspective. Thank you very much, and I always want to thank Dr. Mandal for organizing this meeting, and particularly our guest Dr. Naushad for coming over here, and basically we are getting enlightened by his wonderful knowledge and thoughts and ideas, and we are looking forward to interact with all of you and have future interaction and collaboration. And I think you might be knowing my email ID, actually email address that I have in the first slide, and please don't hesitate to write me and call me. Thank you.